Hello everybody and welcome to the Singapore Virtual Hack in the Box Security Conference 2021 Track 2. It is 1 o'clock, and if you believed that iOS's Appatest API is the silver bullet against client-side data modification, then this security researcher is here to prove you wrong. For our first talk of this conference, is attestation all we need? Fooling Apple's Appatest API. We welcome Igor Lirchikov to the stage.
Hi everyone, I hope you're doing good. My name is Igor, and today I'll be talking about Apple's Appatest API. So I'll tell you how this technology works and what is our options if we want to bypass this check. So let's get started. Currently, I'm working as mobile security expert at Thales DIS. My average working schedule includes reverse engineering, penetration testing, code reviews, and sometimes I conduct security trainings to our developer teams. So annually, I interact with more than 10 different developer teams and support around 30 projects that need significant level of mobile application security. Our today agenda is to discuss what's the Appatest API technology is. So this technology was released by Apple, and in order to help developers to increase the security level of their applications. We'll see what this technology is, what's the right motivation to implement and start using it, and most important part, we will see how actually good it is and what is the current bypass possibilities for potential attacker. This talk is mostly for mobile application developers and defensive teams who consider on implementation of additional protections to their anti-tampering mechanisms. I think it's necessary to describe a potential use case for this technology, so you can get to the point yourself when you can say, like, God damn, I need to have this technology in my app. So, because using something related to security without exact understanding of how it works can give you a false sense of security, which is kind of not good at all. So regarding the topic coverage, I want to declare that this talk is focused on client-side security of mobile applications. So it's mostly about the things that happening on the user's mobile device. But however, we will see how client-side security part could be improved with the server interaction, because Appatest API is not a standalone solution and requires you to be connected to the internet. Now let me name those client-side protections that mobile application developers want to implement sometimes. So maybe based on the requirements or recommendations of different standards, we know there is a wide range of protections, starting from most popular things such as basic SSL pinning or root or jailbreak detection. And it goes to more advanced things, including source code obfuscation, hooking and tampering detection, and other detections aiming to make hackers' life harder. And since we are talking about anti-tampering defense mechanism, it's good to elaborate what tampering is. So tampering is the process of changing a mobile application. For example, during the penetration test, an application might refuse to run on your jailbroken test device, making it impossible to complete some of your tests. And in such case, you will want to change the application's behavior and just turn off this root detection check or jailbreak detection check. And yeah, maybe another example that you should be aware, because it's more harmful. Sorry. For example, crackers or modders can modify your application to enable premium features without paying for that. And obviously, anti-tampering functionality protects the application against such kind of modifications. It monitors the integrity of the application state and environment in which it is running. I'll definitely recommend you to visit Avasp MSTG website. It has a lot of information and detailed descriptions on tampering and anti-tampering techniques. So you can find it there. Now I want to quickly name currently known and popular protection methods against anti-tampering, which are always implemented on the client side. First one is the signature check, the most trivial one. It checks the signer's certificate, and this approach could help you to detect the modification applied to the original app once it's been resigned. Second one is a code integrity verification. It checks whether some specific part of the code has been tampered with by computing its signature at runtime and check it with pre-computed hard-coded hash of its content. And the last one is a resource integrity check. It verifies the signature of specific resources at runtime. For example, these resources could be an image or other assets inside the application bundle. And unfortunately, in the end, attackers always wins and bypass these kind of checks. This is particularly true in the client-side security if we are talking about. So, well-equipped attacker has a natural advantage always. And once the protection mechanism is well studied, nothing stops you from switching all protections off. And the good news is that dealing with multiple protections sometimes is highly complex and could take a lot of time and definitely money to spend. And the state-of-the-art client-side protections are really hard to bypass sometimes. You can't just switch it off using known methods or standard tweaks and tricks. To defeat them, you really need to go through a really meticulous manual analysis, I would say. All right. If we can trust the information coming from our device, and client-side protections eventually could be just switched off, so maybe we can rely on our backend in this case, or even Apple's backend servers. So yeah, I think you get the point. And we're going to talk about Apple App Test API. So, and when Apple announced it, my first impression was like, yeah, that sounds interesting. And our developer teams would definitely be grateful if they don't need to code the whole verification logic on the back end from scratch on their own. So let's see what it does. And finally, yeah, it was a quite long intro. We can start discussing the technology itself. So App Test API was announced and released 1 year ago. and official announcement says that this new app-attest API helps protecting against security threats to your apps on iOS 14 or later, reducing fraudulent use of your services. And with app-attest, you can generate a special cryptographic key on a device and use it to validate the integrity of your app before your server provides access to sensitive data. All right, reducing fraudulent, it says. This description is quite short, and if you don't understand what it exactly means, I can say you're not alone here. So yeah, initially it was quite uncertain to me as well. I checked the documentation, all related articles and presentations from WWDC 21, and it still wasn't clear. So yeah, I was like, what exactly this technology is doing? And is it anti-tampering, or how can I implement it properly? Do I need to code my own detections to support this technology, or I can use it as is and just stop worrying about all these hackers around after I implement it? So, okay. Then I thought the best way to deal with all these assumptions is just to implement this technology on our own and test how it works and whether it's possible to bypass the detection check. And as I said, app-attest is kind of relatively new technology. And first of all, we need to make an intro to this problem. On the screenshot, you can see the default image of interactions between application on client side and backend on the right side. You can use the app-attest class to generate a special cryptographic key on the device and have Apple to verify the validity of that key on their backend. So then you can use that key to assert the validity of your app whenever you request sensitive data from your server or want to record some value on your backend. Now let's talk how it exactly works, because it's kind of unclear from start. During my research, I've made a sample app to understand how the whole concept is working and did a little portion of reverse engineering to see what is happening on the device when we're interacting with the API and what could be altered on our side. This application is written in Flutter. I tested it on iPhone 8 under iOS 14.0.1. And yeah, forgive me for that, but I hard-coded some values that depended on backend interaction because I didn't coded a whole implementation of backend server during this research. But yeah, on the screenshot, you can see that functionality is quite simple, but that's enough for our evaluation. And later on, in the end of this talk, I'll share the link to my GitHub page where you can get the sample app and source code to test your own bypasses and maybe other test cases. All right. It's necessary to say that in the whole process, 3 parties are involved. First is a mobile device running under iOS 14 or higher, then backend server under our control, and third party is Apple's backend server. And yeah, now let's see which steps we need to do to complete the attestation process and start signing our outgoing requests. So on the first step, we are generating initial key value, which is unique to the application and contains device identifier. After we call generate key function, it creates cryptographic key using secure enclave processor. And secure enclave is a hardware-based key manager, which is isolated from the main processor. And from my point of view, hardware-based cryptography, like without leaving a device, it sounds safe enough, sounds good. Then, after we generated this key, we request generation of the challenge on our backend server, just to stay protected from replay attacks and as additional trusted source of data we're interacting with our backend. Yeah. So during this step, we are generating a hash value, and we will be using it as a parameter to the attest key function call on the next step. So in the right corner, you can see the example of this hash value. In our testing app, this value is hard-coded, which makes it vulnerable to replay attacks. But fortunately, this type of attacks is beyond the scope of our research. As I said, on step 3, we need to call this attest key function in order to receive attestation object from the Apple's backend server. So this function, as you can see on the screenshot, it takes 2 input values, the key ID value that we got on step 1, and this anti-replay hash from our backend. So Apple recommends to use SHA-256 hash value, its implementation from CryptoKit. So you're willing to decide how you want to implement it. And yeah, then step number 3, after we call this attest key function with all necessary parameters on our iPhone actually sends outgoing requests to Apple's server. And in the response to this request, we receive attestation object. It's a really, really huge piece of data. Even won't fit in the reference corner. So yeah, it's cropped here. And what is this attestation object actually? So attestation object contains information about device hardware of the requester, application bundle ID, and other sensitive values. And it's very important to parse this attestation object properly on our backend server, because one of bypasses that I encountered was related to incorrect processing of this data. Then during step number 4, we send values generated during all 3 steps to our backend server, where attestation object is the resulting value from step 3. KID is a value generated during step 1, and challenge is a client data hash value from our backend server generated during step 2. Then during step 5, we need to verify the attestation object on our backend. So we need to decode it as a CBOR compatible format and store this data on our server and link it to the corresponding user. So you need to validate the team identifier and bundle identifier, so they must comply with the signature expected for your application. Now let's talk a bit more about these validation steps, what this CBOR thing is, and which values we need to take care of and interpret properly. After you stored the attestation object on your backend, you need to decode the attestation object using CBOR parsing library, as I said. Sorry for this, for me repeating myself. You can actually check the example of this decoded object in the end of step 3. And yeah, first step, you need to verify X5C value, that it contains app-attest root certificate, which is publicly available to be downloaded. You can find the link in the documentation. Then you parse this app-attest root certificate, obtain the value of credcert extension. After that, you create hash of the public key in this stored in this credcert and verify that it matches with the key ID identifier from your application generated during the step 1. After that, you compute the new SHA-256 hash of your application's ID and verify that it's the same as the authenticator data's RPID hash. I don't know why, but still it's necessary to verify that authenticator data's counter field equals 0. Have no idea why they recommend to do it. Then you need to verify the AAGUID field. So it's either app-attest develop if operating in the development environment, or app-attest followed by 70 bytes if operating in the production environment. Actually, it could help you to detect whether possibly tampered attestation object was incorrectly assembled using maybe development certificate or something. So it could help in behavioral analysis. So then you verify that the authenticator data's credential ID field is the same as the key identifier from step 1. And after successfully completing all these steps, you can trust the attestation object. Actually, yes, I agree that recommendations from Apple is kind of good and efficient, but the problem mostly can occur on integrator's side if validation is not properly implemented. Then step number 6, it's kind of optional because but you still can use the receipt that was extracted from attestation object during previous step and send it to the Apple server to get the metric, as their documentation says. What is the metric, you would ask? So Actually, response body from the Apple server has risk metric field, so which is integer value that indicates the number of attested keys associated with the given device over the lifetime of the device. So kind of small piece of knowledge, in my opinion, but still maybe it become more useful in the sometime in the future if they add more fields to this metric. Next one, server to server interaction. Here you can see that it's declared that this metric can grow if user reinstalls the application, restores from a backup, or transfer a device to another user. So yeah, for privacy reason, app-attest keys stored on device, they don't survive these events, and you have to generate a new key on the same device. And this metric from Apple could help you in identification of potential API abusers. However, in the end, it's just a number, and only you decide whether you want to interpret this information as something suspicious or not. And it's necessary to remember that Apple doesn't provide a solution. It gives only additional source of information. Step number 7. As you might note, we cannot generate attestation object each time when we want to verify the request because it would mess up the whole metric on Apple backend. So we will use another object related to attestation object. It's called assertion object. If you successfully verify the attestation object on your server during the step number 5, you can associate the key ID, which you got from the step number 1, with the user's device for the future reference. You need the key ID identifier to generate assertions. Or in other words, you need this key ID identifier to be able to sign requests going to your backend servers. Actually, assertion object and attestation object are both coming as CBOR objects. So far, I saw almost every popular programming language has its own library to parse and decode CBOR. And yeah, even the sort of fresh technology, Flutter and programming language Dart has its own CBOR decoding library. And if you're interested in analyzing its content, I've implemented inbound CBOR decoder inside my sample application, and you can play with it if you want. And if I remember correctly, step number 8 is the last step. Finally, we need to verify this assertion object on the backend. So after receiving the client ID data, which is request body and the assertion, you need to verify and decode the assertion to ensure it uses the CBOR data format and has the expected contents. After assertion is verified, you can trust the request and consider it as not tampered. Let's quickly go through the process of assertion object validation. And I can say it's mostly the same with the attestation object verification. you can check that incoming server request was signed with previously generated private key and all necessary hashes are the same. And after assertion is verified, you can trust the incoming request and consider it as not tampered. All right, finally, we finished with the implementation process of this technology. But does it mean we are protected now? I mean, if we passed all these 8 steps, here you can see some assumptions and remarks made by Apple on their forums and even in documentation. And to me, it sounds really confusing because it's almost impossible to say, for example, that you have 100% evidence that you know what is going on at user's device, that it's not jailbroken or it's not tampered. How could you say that it's not tampered from the very beginning? Yeah, on this screenshot we can see a kind of not clear acceptance of the fact that they can't do much against jailbreaks in terms of detections. And yeah, somehow you need to figure it out on your own, probably. And one more funny slide is a brilliant official answer about possible hooking or patching of the attestation call. And yeah, frameworks engineer says literally nothing you can do with it. So don't be surprised that you have to implement much more detections apart from this app attestation thing. Now let's talk about all these bypass related scenarios. All current bypasses are quite simple and depend on the fact that app attest can't detect whether device is jailbroken or application was tampered before initial installation on the fresh device. Neither detect hooking frameworks, which are modifying behavior of your application during runtime, during its runtime. We don't even need to hack the key generation algorithms, break the cryptography, because it's really tough. It depends on secure enclave, and in our case, definitely not that efficient to attack through this channel. So we don't need to do that because we can abuse the developer's logic. Fortunately, you saw there is 8 steps and there is plenty of space to make a mistake during the implementation. From my experience, I can say that I haven't seen a single application which properly implemented app attest yet. In all instances, it was possible to bypass the check. I mean, literally, you can bypass it by abusing its logic. And here is the cases. Number 1 is quite simple. Do you remember we need to start the attestation process during step 3, which requires internet connection. It's kind of crucial step. So we can just drop outgoing requests by configuring the meeting proxy or using Frida hooking framework. And in some cases, application logic handling this case as a scenario when Apple server is down or not accessible, and continue working with when internet access disabled, for example. In this case, bypass works actually. And yeah, sometimes it requires more throughout checks that validates that you can interact with your own backend server, but somehow you cannot interact with Apple's backend server. Yeah, which means something is going wrong, but none of examples that I saw had such type of check on their side. Next scenario is so yeah, my favorite one, which works every time as of today. You need to return that iOS version is less than iOS 14. You know, many developers, they are not ready to drop all users who are using devices below iOS 14 yet, and it may take few more years to make up a test API usage mandatory on their side. So you can just hook the value, the return value of platform API when it checks the iOS version, and you are able to bypass this check. It just won't trigger the whole key generation logic. Yeah, here is a small piece of statistic regarding that. So it says that 10% of all iOS and iPad OS devices, which is around 100 million of unsupported devices, are below iOS 14. And I think this version related bypass will be most efficient thing for some time until iOS versions less than 14 is end of life and not supported anymore. I've heard an opinion from one application developer that Apple has an ability to validate the signer's provisioning certificate on their backend before returning the attestation object. It was his understanding of the app-attest API description. So in simple words, his assumption was that Apple can see that I resigned the app with the developer's provisioning certificate, with my own certificate. And Apple could detect it somehow and just don't allow me to start this key generation process. And as you can see on the screenshot, it was kind of wrong assumption, and anyone can modify your app, patch its logic, and resign it, and still generate valid attestation object after all. And yeah, it will be assembled with wrong values to your backend, but at least it still remain valid in terms of its format and Apple's signature in it. So if you parse it right, it won't be valid on your backend. However, as I described before, once I saw the case when attestation object was not correctly processed, and literally any value was correct for to the backend until it's properly packed CBOR object. So please remember to implement and test everything as it's recommended in the documentation by Apple. Okay, now I think it's time to summarize all the benefits and bottlenecks that App Attest API gives to us. So on the bright side, we can use it definitely against the replay attacks if we trust the whole process of key generation and stuff, definitely. Some companies can really benefit from implementing this fraud metric analysis, and maybe Apple can extend the list of metric data in the future. It really could increase anti-tampering protection as additional layer of security by leveraging bypass complexity for already implemented RASP checks. So in other words, I want to say that if you need anti-tampering, you still have to code a lot of things on a client side. And maybe in the future, it really might become an industry standard once it's supported by 100% of iOS devices. Why not? I think it will be harder to find logical bypasses for this technology. And now it's time to summarize all the bottlenecks. On the constraint side, it's still not possible to validate if application is already running on compromised device. So if device has been jailbroken after the key attestation, all the new assertions might be tampered. So, and you won't detect even using this Apple's fraud metric, because you can just hook the application behavior during the runtime, and the outgoing request will be signed on using the valid attestation. So you will trust the object on your backend. So there is no reason to try to break the signature method if you can just tamper on values before signing the request. Then it's kind of useless as of now, because it has multiple design issues, and success of this implementation strongly depends on the integrator. So there is a human factor in it. One more limitation is that if you're developing app extension and want to use the App Attest API, you can't, because it's not supported. And I don't know whether it's a big concern, but you still depend on the third party. You depend on Apple's backend server, and if it's not working, so I understand it's unlikely it won't be working, but if it happens, it means your app is not working as well. And as I said, the number of unsupported devices is still very big, so developers are not ready to drop all these potential users to their app to improve the security. And now it's time to decide to answer the question if it's worth to implement this technology or not. Actually, yeah, the simple answer is that you need to listen to your security experts, security champions. You need to understand your risk level and threat model. And if you really decide to implement it, and if you are confident to have it properly implemented, you have to be ready to work with all possible caveats on your own. So as we just discussed, it won't help you. So the APA test won't help you to identify if device is jailbroken or not. So, which means you have to implement jailbreak detection, and it have to be on client side, which, as you remember, could be easily tampered sometimes. But okay, then to fight with runtime instrumentation and dynamic analysis, you need to implement your own hook-in detection and debugger detection checks. And still, even despite APA test is sort of anti-tampering solution, you need to have client-side anti-tampering protections to make it harder to statically patch your app and resign it. Because you remember the bypass scenario number 2 or number 3. Yeah, it was number 3. We just patched it and resigned the app. So APA test won't even trigger it in this case. And in the end, definitely quite important part to make attackers' life harder. You have to implement obfuscation layers. It must be strong enough to increase the whole analysis, the complexity of this process. So in conclusion, I want to say that we can't create trusted anti-tampering check using only this API. So evaluated solution should be backed up by current client-side protection mechanisms, which are well known and described on the different resources such as Avast MSTG. So I'm talking about anti-tampering, jailbreak, hook-in detection. It will help you to ensure that information provided by APA test is not modified in the first instance. Sometimes even prior the first usage of this APA test API. We also have to take in consideration that this API is available only from iOS 14, and we have to wait until it supports vast majority of Apple devices, and because of that, I recommend to implement this technology only in experimental mode, and definitely following the close interaction with your security team, because it's necessary not for every product. It costs money to achieve the sufficient level of protection. So make sure it's really necessary for your project before starting playing this cat and mouse game with the hackers. And trust me, they are always competitive, always find bypasses, and you need to improve your protections continuously. And definitely, I believe there is always a room for improvement. So if you feel that something could be improved in this analysis or in the whole talk, that is the explanation part, so don't hesitate to reach out to me. I'm planning to continue keeping an eye on this technology to see how it evolves, or whether other bypass scenarios are possible. Here you can find the link to my GitHub repo with all code I used for this presentation. As I said, my implementation doesn't have a full-fledged server side. So if you really need it and don't want to code it from scratch, please take a look at this nice second repository with the server-side implementation. It's written in Kotlin. And yeah, you may want to check OWASP MSTG if you want to know more about attack techniques and protections that we discussed today. And the last batch is related to official documentation from Apple. Kind of must read if you want to get more details about this technology, but be ready that documentation sometimes is confusing. And that's mostly it. I want to say thank you for watching this talk. And yeah, huge respect to the organizers of this conference. So for many of us folks interested in cybersecurity all over the world, yeah, we are happy to have such events during this COVID pandemic time. Yeah, hope to see you IRL in the maybe next year. So yeah, goodbye everybody and stay safe.
Thank you, Igor, for your time and talk about the Epitest API. Now stay tuned for our next talk, Taking Guider to the Next Level by Zhang Zhao Ding at 2.
Hello everyone! I hope you're all having fun at Hack in the Box. It's time for the next talk of track 2, Talking Ghidra to the Next Level, given by Zhan Xiaoding. Enjoy!
Hey guys, what's up? In this talk, I'm gonna talk about our recent work on Ghidra, the reverse engineering tool. Our goal is to push Ghidra to the next level by fixing things, adding features, and introduce more state-of-the-art technologies. Hope you guys enjoy this talk. First, a little bit about me. My name is Ding Zhanzhao, or you might know me as Anthony, my nickname. I work now at the Starcross Technology, responsible for binary analysis part of the Portal Lab. Portal Lab is our lab in Starcross Technology, where we research around topics like API security, cloud security, binary analysis, reversing, and so on. I've been playing CTF for some years till now. Since 2017, some friends and me started Team Rockapig, and I have been playing as Team Rockapig for about 4 years. Since 2019, I started my team leadership of Team Rockapig. Luckily, right after we started Team Rockapig, we were qualified for DEF CON CTF final, and again, that is about 4 years now. Besides DEF CON CTF, we also played many other CTFs and get awards in many of them, such as Zero CTF, WCTF, and many more. Usually, when I don't play CTF, I do some open source developing, especially enthusiasts in reverse engineering and binary analysis tools. And that's why we have this talk today. In this talk, we will be first talking about vanilla Ghidra, how is it like in my personal view. The next thing I'm gonna present you is my recent work, Beancraft. We will be talking about my dedication and what we have done, what we wanted to do, and the lessons learned along the way. Okay, the first question I want to ask before this presentation is, what are actually needed in reversing? I've been talking about this with my team members for many times. While you reverse, there's a lot of things you might be needing. Things like retyping variables, renaming variables, but first you need the basics, right? Which is F5 in IDA, the decompilation functionality. Time just passes. Many years ago, we still have the gut to reverse any instruction set by just looking at the raw disassemblies. But that time will never come back again. Now, many people just can live without F5, without decompilation. So, let's get real. All analysis we need in actual reversing can be categorized in static analysis or dynamic analysis category. Listing every analysis in these two categories is not quite possible here, since there are so many of them. I listed what is the most important ones. Like in static analysis, a reverse tool must have disassembly to be called a reverse tool. If you are hardcore enough, decompilation is not a must. But people don't do that in this age now. We definitely need decompilation for real-world reversing. As for dynamic analysis, two things I can think of while reversing is debugging and emulation. Debugging allows us to inspect the internal status of the program during the runtime. Many of the time, when the binary to reverse is absurdly complex, debugging the internal is the only technique we left for understanding how it works. You set the breakpoint, run it, check those register values and memory values, and then continue again. Those values can reflect the logic behind the binary. Sometimes you can even guess the algorithm and verify that by inspecting only the internal status like the register values and memory values. As for emulation, emulation is mostly needed when I saw some binary has the runtime extraction technique used. With that, those binaries can prevent you from reading its internal logic without running the program. Or, if you have the time for that, you can just reverse it from the very beginning and completely understand the extraction logic, then do it statically. But that's just a rare case. And since the extraction logic may not be used elsewhere, if you do that, you waste a lot of time on that. Which for me, I think is not needed. So we just do emulation, get the result, patch it back on the binary, and check the decompilation. That is how things work in this age. Consider those functionalities. What do we have now? IDA is definitely the ruler without any question. I can say that its decompiler is the state-of-the-art level, since I know quite some research papers claiming that they have better decompiler compared to IDA, but it's undeniable that IDA has at least the world's first-class decompiler. They have tuned it for many years. One thing I learned in playing with decompiler technology is that making the decompiler work is not that hard. Many people overestimated the complexity of implementing a POC-level decompiler, but what makes it complex is that you need to adjust the decompiler to fit into many corner cases. You never know what people would use the decompiler for. Many algorithms used in the decompiler have to deal with those special cases. That's why you need a lot of time fixing those problems. And IDA, for sure, with these years of fixing, they made the decompiler quite reliable. At least no other project can go beyond them in the industrial area for now. Apart from IDA, we still have some choices, like Ghidra, NSA open sourced, which is our topic. I will talk about it later. Next, we have Binary Ninja. It is a nice project if you ask me. Although commercial, it has an intriguing design of the decompiler procedure. They made it into several phases, and each phase you get the result that you can read. In this way, they don't need to implement a decompiler immediately. During this phase, they gradually make disassembly, graph view, then each phase of the compilation output works, and the APIs are quite complete. But the problem is they don't have it open source and they still need more time to make it as complete as IDA. That decompiler still needs more fixings. It is a binary analysis framework, but as far as I know, they seem to be moving to complete reverse engineering tool recently. The decompiler seems to be commercial while the basic binary analysis thing is open sourced, and the decompiler is not out yet. The last one I want to talk about is Reader 2. I totally like their philosophy. The Unix-style reverse engineering tool really creative. But when doing the reversing, the command line interface compared to graphical user interface is not that convenient after all. During reversing, you may have multiple views simultaneously. One display the disassembly, one display the structures you identified, and even one more for decompilation. If you do that in the command line, you may waste too much time on inspecting those information. So for me, it is interesting but not too good to be used in real-world reversing. And one thing they lack is decompilation. I know about some efforts being made to Reader 2 to integrate Ghidra or other decompilers, but still it is an integration. You need to translate things around several intermediate representations to make things just work. Sometimes it does not work so well. They also provide a graphical user interface called Cutter, but the internal remains the same. You may say that I'm a bit biased, but in real, I just haven't used it for serious reversing tasks. Maybe, just maybe, it is because I got so used to IDA and can't move to a new type of working flow. Anyway, that's my comment. So, to be honest, the only one that I would like to use in real tasks is Ghidra. If I have to choose in those tools except IDA, especially if I wanted to choose between the open source ones. For me, open source is an important issue as sometimes when I got into a problem, I usually don't want to wait for the solution. That would take quite some time. And one more thing, I am always the curious baby wondering what is the cause of such software bug. Not knowing the reason behind the bug is killing me. That's why I always prefer open source softwares. Let's get back to the point. Ghidra is open source in 2019, written in Java and native language such as C++. It actually has not fixed the native languages you can use since the Java would interact with the native language in RPC protocol. This would be talked about in detail when we get to the Ghidra decompiler internal part. What I care is that Ghidra has an almost complete feature set. That is, we have decompiler working, graph view working, debugger working. This is not a complete list. In short, most of the things you might expect in IDA is just there in Ghidra. And the extensibility is extremely good as they use Java for that. I know many people complain about how Java gets unreasonably long, but let's just admit, Java suits perfectly when you need such extensibility. The scripting interface provides you with Java language scripting and the Python scripting with Jython. One thing I can think of that fails is Jython can only support Python 2, and this might not improve in quite some time. And the plugin, import a jar file and you are good to go. When developing the plugin, you have almost the full power of Ghidra. call any method you like. It's just like developing part of the Ghidra itself. Even Ghidra itself uses the plugin system to make the code more organized. Also, Ghidra has a grid architecture that I am referring to the Slay DSL. Slay is a programming language developed in the Ghidra project. It is a DSL describing the relationship between binary, the IR, and the assembly display. In this way, you don't need a meta language to write out logic describing how the binary lives to IR and how the binary should be displayed in assembly languages. You only need one such DSL for that. To make this clear, you write a Slay language code, you get a disassembler and a decompiler. That, I think, is one of the strongest features Ghidra has comparing to other tools. To sum up a little, Ghidra is the only one in the open source world that competes with IDA. Man, how I wish Ghidra is just that perfect, but the world doesn't go that way. Since Ghidra is a project of at least 20 years of developing, the historical issue is becoming its problem. We have historical code in Ghidra, and we might also encounter historical user experience issues. This is one example of the historical code issue. The C99 types are now a standard, but still Ghidra decompiler is not using them but use something in their own. This kind of thing is quite common, especially in the decompiler code, especially about the coding style. Some of the coding styles are proved to be bad practice in these years, but those code cannot go away in the decompiler in a single glance. And because of those code, the developing of such components can be quite hard, which prevents people from introducing interesting features. As for the experience problem, you can clearly see that in the UI interface, right? The UI interface feels so much like I was in the last century. I know some people don't care about the UI interface when reversing generally, but this is just an example. For many people, this is where the first thought about Ghidra goes in. So, I admit that Ghidra is a rather good project, no doubt. It is already nice enough to be used in many of the time. People around me always use Ghidra when their IDA is not working. Like before, when we encounter MIPS binary, we always use Ghidra. But is that it? We just let Ghidra that way and only take it as the replacement when IDA is not working? I want more than that. I want a project in the open source world that can grab some of the IDA users away instead of just staying as a replacement. I know that's a long way to go, but we need to work out the first step. The plan is simple. We just modernize everything got into our site. Modernize the experience, UI if you want an example, add modern features apart from the vanilla Ghidra ones, and hopefully we can also refactor the code to make that modernized as well. But that I know would take away quite some time. So we might do that gradually, step by step, and for each step, the project should stay working. We never thought about totally start up a new project and just give up the official Ghidra. That would take too much. And we also don't have that manpower for maintaining such a huge beast. So what are the differences? What I think is we improve Ghidra where we use it. In this way, we know what Ghidra lacks, and since we know the internal of Ghidra, we know how complex it is to implement the feature we want. We play CTFs, and that can be a quite good experience for tuning Ghidra. It's like extreme tests. My wish is that by using this way of improving, we can better understand of what we need as we are both the developer and the user. I know some of you might think, okay, so you have ideas about Ghidra, you can develop those features and you don't have enough manpower to develop your own. So why not just contribute that to the main repository? Well, that would need some explain. I'm not gonna deny that initially I wanted to do that this way, but later I found that people all have different tastes. This happens when adjusting decompiled coding style or user interface. There's no such thing as ground truth in decompiled code if you ask me. I think the decompiler is never about recover the original source code with only the binary, but to give you more insight of how the original source code works, and the decompiled code could make your life easier since you don't need to read raw assemblies for understand that. That is, we do not have a style that we all accept. Thus, we always have the choice to make it style A or style B. This is the same for UI as well. And for this project, when I decided to make it separate, I was thinking about making it a different choice. We have a different flavor, and if you don't like Ghidra's solution, you may choose ours. One more choice is always good for this world, isn't it? To ease the maintenance, we will be following the upstream closely, and if some of our features not about flavor issue, we will still send that to the upstream. So I'm not starting up a new religion like Beancraft versus Ghidra, no worry. Okay, the name of the project, as I mentioned, is called Beancraft. So what is Beancraft? I designed Beancraft as a collection of Ghidra related projects, or a Ghidra release. Now, Beancraft has several projects. First is our main topic today, GhidraCraft, which is a fork Ghidra following what rules we talked about already. The second one we have is Slaycraft. I already mentioned Slay DSL, about what it is in general and how it provides the extensibility. I believe you already know how great it is, but unfortunately it is designed to be used in Ghidra internally. So Slaycraft is to save you from that. We provide APIs in different programming languages to use the Slay engine. With that, you can do what Capstone is capable of, and you even get the IR out of it. And PickledCraft, a Rust API to abstract away Ghidra's decompiler. We tend to use that to complete our refactoring job and to split the vanilla Ghidra decompiler into several reusable algorithms. It is still not completed yet, so we will not talk about it in detail today. Beancraft is the name of the collections. The reason we organize it this way is we may have many more projects according to our plan, and many of them might be closely related. So this collection could give you index to those projects. Let's get back to the GhidraCraft, the main player we are gonna talk about today. Till now, the modernization is still in progress. We have already done several tasks which I would like to share. First, we have the decompilation improvements. This is more like a normal improvements, but during that, we face the flavor issue and tuning the style our way. Next thing to have is pickled patch feature. This is the very first feature apart from the improvements. You will get an idea of why we choose to do that shortly. And finally, we have partially modernized UI style. Let's dive into the first part, about the decompilation. You see, every time the IDA upgrade is out, it would have an item saying that it did minor decompiler improvements. Before doing this, I always think I can solve so many problems in the decompiler. It turns out I was being too young. The decompilation process is complex. The code, the algorithm, the architecture are all complex, especially when it is in C++ without modern C++ features. References and raw pointers are everywhere, and Ghidra even did a using namespace std before every source code. I have to admit, this one is quite difficult to tune. I will talk about some of it to give you a basic idea of how difficult it can be. A little bit about Ghidra's decompiler first. The overall structure is clear, nothing special. If you know that, this is exactly how VS Code language server protocol would do. A custom RPC protocol is used to interchange data between the Java side and the C++ side. Actually, the Ghidra requires you to use such a way to connect Java world and native world. That's why when you need to write a plugin with native languages, you can always choose the one you like, as long as the RPC is working. Anyway, the RPC protocol used by the Ghidra decompiler is in XML format, mixed with binary values to mark starting and ending of a single packet. Each time Ghidra decompiles any function, it launches the process, send the previous result in XML format, and the C++ executable deserialize it and does the decompilation, send the decompiled result back in XML format. Just to mention that the XML format is treated in Ghidra code as if it were a string in many places. So if you'd like to add one more object that is both serializable and deserializable in Java and C++, you have to define the serialization and deserialization yourself. That is one place where your code gets very large. About the C++ world, it is more like a traditional compiler architecture, just like LLVM. We have the actions, which might be called passes in LLVM or some of the compilers. The global context is called architecture to provide architecture-specific information. Per function data is called just funcdata. Almost all the data in C++ world, like architecture or funcdata, is serializable and deserializable. That is a requirement for Java world to have full control over C++ decompiler. You see the problem here. There will be many code describing the serialization protocol, and we don't have a DSL to describe such thing to make life easier. Once the protocol requested some result, the actions are run. Each action performs one of the steps required by the decompilation. The actions work on the IR, manipulate them, extract information, record it into the funcdata or architecture. Finally, when we are all done, the pseudocode is generated by a language printing component in XML format. Then the result is fed into the protocol again to reach Java world. As you can see, the central of the decompiler is the IR they used, called pcode. The actions perform manipulation by inserting, removing, or modifying the pcode IR. The IR is designed to be suitable for low-level analysis. It was originated from an IR between the translation of two instruction sets. They model all variables as var node, identified by three parts: the address space, offset, and size. The address space is just like a piece of memory, or a huge array if you like to think it that way, along with a name. Some names have special semantic like register, RAM, which is used as memory. Temporary values are in unique space. Even the constants or immediates have a space, named const. But that is a special space, it is not a huge array. The offset in constant space is treated as the constant itself directly. One thing I feel quite intriguing in this kind of design is that how they model the registers as just a plain piece of memory. Normally, registers are modeled as it is. We have register names and size for each of them. But if you consider the overlapping between registers, that kind of model could just make things really complicated. As for pcode, we see that, for example, the zero offset in the register space under x86 is RAX. Since we have the overlapping, EAX register is easily modeled as the same offset but different size. Operations are just normal operations like you may encounter in any RISC-like instruction set. There are some special operations we need to care about, for example the multi-equal instruction. This instruction is not intended to be used after the lifting, but to be used during the decompilation. Multi-equal instruction is the fine node of SSA form. It is internal to the decompiler itself. By using such instructions, the internal form such as SSA is still invalid pcode, and we don't need a different data structure to store them. This is the overall structure of the decompiler, the actions that are run when a function is requested to be decompiled. It would be too much to talk about this in detail, since it is not the goal of this talk. I am just putting it there to have you understood how complex the decompilation process can be. So let's get back to our tasks. First thing to ask is, what things should be done to improve the decompiler? To balance between the implementation difficulty and its benefit during real-world reversing, we have selected out some of the goals as the first step. Those include the appearance of the magic functions such as concat or the ext, the lengthy default variable names, the analysis failure, and more minor problems. About the magic functions, this happens a lot in Ghidra. Sometimes, when we reverse binary, those functions like concat44 or zext8 just come out of nowhere. Since usually we don't have those functions in C language, without documentation, we will definitely have a hard time guessing what those mean. It turns out, they are just pcode that is not translatable. Concat or zext is the pcode instruction. For example, the concat44 is just concatenating 4 bytes and 4 bytes to form an 8 bytes variable. Comparing to IDA, I found that IDA tries its best to not show those magic functions, but this does not seem to be the same in Ghidra. And following IDA's idea, I think we have a better way of showing this. As a result, we added a rewrite rule to convert the concat instruction into typecasting and normal arithmetic operations. Just to mention, while the rewrite rule, we found Ghidra decompiler does not have an abstraction of rule matching and rewriting like in LLVM. LLVM has an AST matching DSL, which makes writing such matching convenient, but in Ghidra, you are on your own. In the future, when we decide to refactor this part of code, we might add that. About the default variables, current Ghidra's variable names are way too long compared to IDA. I totally understand the reason they do this, since they do not choose the way IDA did, use a shorter name and add a comment introducing extra information like the offset of this stack variable. They decided to add everything in the variable names, but the outcome seems to be too verbose when reversing a large function, and since we get used to IDA's way already, we decided to change that. This is not difficult, but just a user experience issue, and we made it into an option, so we give you the choice. Okay, the next thing we have is what matters the most, the analysis failure. Take a look at this picture. This is from a DEF CON course challenge this year, called RAD. The challenge is written in Rust, and as you can see, the output code is totally not readable. There are plenty of assignments to an array that appears to be a magic number. If you take a look carefully, you will notice that this assignment all happened before a call to a function. And yeah, as you might guess, this number is where the function should return, i.e. the next instruction address after the function call. All other stack variables have this problem as well. The simple operations are translated into a store into stack space. There's a variable that contains a lot of f's in its name that is actually the stack base of this frame. So all other stack variables are not analyzed out. Instead, they are all translated into the relative addressing with reference to the stack f blah blah variable. Also, all the function params are just gone. After that CTF, I played with it a little bit and fixed these two problems: stack variable analysis failure and function params analysis failure. At the time of DEF CON, we used IDA to reverse this challenge. IDA also suffers from the function params failure, but is doing better in the stack variable analysis. Actually, that is one of the most important problems, as without the stack variables, the decompilation result is not useful in the end. Especially because of Ghidra's mechanism, you can never get rid of this assignment of the return address. Let's talk about the stack variable analysis problem first. To understand this problem, you will need to first understand how the stack variable analysis in Ghidra works. I'm not gonna lie, this takes me quite a while. It is not because Ghidra has no documentation about it, it is because the documentation is not something for me, I think. You may need to read the code again and again, and the documentation as well, to fully understand the mechanism. Anyway, about the stack variable analysis in Ghidra, the actual algorithm is way more complicated than this, but this should give you the idea. Ghidra first marks out the input RSP, the initial RSP value of this function that is used with but not defined. Let's give it another name, RSP0. Note that Ghidra does not do any interprocedure analysis, which means when it decompiles a function, it does not take any look at any other functions inside. After that, Ghidra will run a constant propagation procedure. This constant propagation procedure is not specific to this analysis, but its result is used here. Then, Ghidra thinks, after the constant propagation, all the RSP values should be marked now, in the form of input RSP or RSP0, adding a constant. If it is not in this form, for example, if you got RSP0 multiply something, then it is not possible to be treated as stack variables. And what causes the problem? Initially, at the very beginning of the Rust compile function, there's an RSP constant instruction. After the AND instruction, the RSP values are now not RSP0 at a constant. What we have is RSP0 and a constant, then add another constant. In this form, Ghidra thinks, okay, you are not a stack variable, then how about we treat you as an offset into the variable that equals RSP0 and C. About the magic numbers, these are return addresses. I already mentioned that. The reason behind it that Ghidra treats the return operation as if it were an indirect branch. So it does not do anything about store the return value. So the store return value operation is explicit. Once the stack variable analysis fails, it has no idea that this is a store of a return value. It sees it as a normal assignment. That's why we get our final decompiled output full of such return address assignment. As for the empty params problem, this one is not that annoying, but still I decided to fix it since I met it. That is my philosophy. At least I should fix things I met. This problem is caused by the dwarf debugging information handling. Usually, as in C or C++, when you do not specify -g to enable debugging information, the debugging information is not generated. But Rust does this in a different way. It always generates the debugging information, but if you do ask for optimization, it generates incomplete debugging information. Params information is one of the examples. It generates function names but not params. Then Ghidra's dwarf handler thinks we have a function but no params. That gives us this situation. IDA also suffers from this problem. Rust is just not that supported by the reverse engineering community for sure. So next time you want to protect some important code, just use Rust. The result is that we fixed this by adding this special case, and the pull request is already merged into the upstream. And we have minor bugs such as the wrong display of the string in the decompiled panel. As I remembered, IDA also suffers from this problem. Golang and Rust compiled binary has a different layout of string. Multiple strings are put together, and that confused the decompiler display. This is not a bug worth noting too much. The fix is still in the pull request list of the upstream Ghidra. Okay, enough of the fixes. Let's talk about the feature. A feature called pcode patch has been added to our GhidraCraft, which is responsible for modifying program semantic. What makes things different is that we support both manual patching and scripted patching. Many of you might already know that. IDA also has such a functionality, but all in all, we are still different. IDA calls this IR patching microcode API. You can insert a phase into the decompiler pipeline to manipulate the IR when decompiler is run. Our way of patching is not in the decompiler pipeline, but instead before the decompiler is run. This allows us to achieve manual patching. By right-clicking on the pcode, you can patch, insert, or remove the pcode before the decompiler runs. In this way, we get a more interactive analysis loop. We inspect, patch the pcode, then inspect again quickly. No need to write the script for that. The manual patching follows what is called raw pcode format. The pcode instruction contains var node and operations. Each var node contains 3 parts: the name, offset, and size. The operation names follow Ghidra official reference to pcode. Here we have an example of this syntax. In this sentence, we are adding 2 constants. First one has offset 8 and size 8. Second one has offset 16 and size 8. As I said before, the offset to the constant space is the actual value of the constant. Then the value gets assigned to the unique space variable offset 0x1234, which should be a temporary value. As for scripting, you need to have the instruction instance to patch pcode. This is because pcode is always attached to a single instruction. Then you can parse the raw pcode syntax with pcode raw parser to get a pcode array and patch it on the instruction to modify its semantic. When I initially wrote this, I have thought about 3 use cases. First one is to quickly modify program semantic that we have already discussed. You can do things like modify part of the decompiled program by its pcode, then inspect the result instantly. I know that if you patch the bytes on the instruction, you can also get similar result. But the difference is, sometimes there are only little space you can put in the instruction bytes. But if you patch the pcode, you don't need to care about that. Another thing to mention is the obfuscation. The same as above, you don't need to worry about length. That is the major reason we still provide a scripting interface. And the final one, I like this one the most, is to allow total custom decompilation. You provide Ghidra the pcode IR, it gives you the decompiled code. I really like this use case. We will be talking about it later in detail. A simple example of the first use case. This is a real example of my reversing a CTF challenge. The challenge uses runtime extraction techniques to extract the basic blocks one by one. I used the emulation technique to deal with that, and successfully got all the basic block instructions out. The next problem I have is to connect those blocks together to get the full decompilation. This should be normal if you could just patch the jumping instruction at the end of each basic block. However, this is not the case. The The challenge uses an ending mark to mark the end of each basic block, and a handler to handle such ending mark when it is there. Long story short, I was left just 2 bytes, but I need to patch a jumping instruction there. Then I used pcode patch to just patch the branching in pcode, and I got the decompilation working. Deobfuscation is nothing special. To demonstrate that, we wrote a simple script to deflatten the control flow flattening contained in the OLLVM obfuscation framework. This script is provided in the GidraCraft repository as well. Searching for LLVM in the script manager, you will find it. It works under multiple architectures. Now let's get to my favorite part, the custom decompilation. You patch the IR, get the decompilation. Let's think about it first. What is the normal way of decompile a custom instruction set? Because of the SLAY engine requirement, we at least need to specify how to parse the binary into a tree, how to display that tree, that is to display the disassembly, and then to translate the tree into a piece of pcode. This is not a problem if you are really dealing with an instruction set, but what if you are not? That is where we need the custom decompilation. Actually, this should be just a trick leveraging the pcode patch functionality. To do that, you can set up a new segment, add an op instruction there, then patch the pcode to that place. Once you've done that, you get the decompilation. In this way, what you are doing is bypassing this SLAY engine so that you don't need to provide the complete SLAY DSL, which sometimes is an overkill, or sometimes you just can't do that. Under some circumstances, you might be needing that, like a weird instruction set. You know how it can be translated into pcode, but the complete SLAY is hard to write. For example, if your instruction is in text format, no binary representation, then the SLAY engine is getting troubles. One example of that is the brainfuck language. It is an SOLAN. I've picked up its semantic here. You can see this language contains only several symbols, and it is quite low level. Each symbol is like a single instruction within an instruction set. We should be able to decompile this thing, but the problem is, if we'd like to do that, we have to go through the whole SLAY pipeline and write a SLAY DSL for that, which I think is an overkill. And brainfuck is kind of a special example that its symbol is all single characters. If you insist, you can still get SLAY working for brainfuck, but it is possible that we may have such an instruction set that has only text representation, that you cannot directly use the SLAY engine to handle it. This happens a lot in CTFs. So, what the result is like. These two pictures show you the result of decompiling a Hello World program in brainfuck. You can see that the looping is successfully translated, and by doing a little bit more to add a call to the write instruction, we made this even look better. I definitely would like to reverse this kind of code instead of original brainfuck code. I know you might argue that by translating the code into x86 or ARM, you can get this result probably as well. But the thing is, in that case, the temporary variables, like we used in unique address space, the one that I mentioned to store the temporary variables in pcode, you have to manage that your own. Not to mention that pcode is designed to be used between languages. It is no doubt more easy to use to translate into. As for the UI, we have also did quite some jobs to make UI feel better. Things including fix some classical stylings and add configurable color setting support. Ghidra has a lot of colors, and they are not equal. Some of them are configurable in the settings. A color picker is implemented for that. Some of them just follows the underlying Java Swing theme, but that's not all of them. Some of the colors are hard-coded into the Ghidra code. I don't know about the reason they do it initially, but that happens. It is not configurable, not in the settings or any kind of configure files, just hard-coded. The Java Swing theme is possible to be switched in Ghidra, and if you do that, those hard-coded colors appear to be really annoying. Some of them mess with the background and you can't see any characters. That's why we make that configurable with a color.properties file. But unfortunately, we can only do some of the adjust. The colors are too many in Ghidra and we can't just deal with it right now. We might use some helps on this. This is the demo of the UI for now. It is not possible to show you all the changes, but I think you get the basic idea. There's not much to talk about how we feel about the new UI interface. There are still a lot of things we can do. Fixing colors, dealing with Windows 98 styles, we have fixed some, but not all. This is not a really hard job to do, but we do need manpower on this. And what we have next is the GrioVM integration. This is a planned feature, but honestly, I just can't get it done in time before the presentation. But I think the idea is intriguing, so I decided to share it with you guys. What is GrioVM? It is one of the state-of-the-art technology in compiler area developed by Oracle. The idea is quite fun. By reuse Java hotspot JIT engine, GrioVM is able to JIT compile any programming languages, even low-level ones such as LLVM. What I like most is about the analysis part. Once you have the language implementation, it provides you with the general instrumentation framework, and the instrumentation should work under JIT. To us, this is definitely good news. We finally have the tools to achieve JITted binary emulation without too much of a work with the help of the GrioVM. Current implementation of the emulation in Ghidra is a nightmare. It is embarrassingly slow, and with the help of the instrumentation framework, we might even reuse the analysis designed for other languages. We need to have that consensus. Binary analysis is an extremely small area comparing to general programming language analysis. No doubt, those tools designed for other languages must have a better maintenance, and luckily, with this technology, we are finally possible to reuse them. We might have free tinted analysis or even symbolic execution for free. Well, if not, we might consider do that anyway. GrioVM provides a language implementation framework called Truffle. Truffle eases the usage of GrioVM by allowing us to write the interpreter, and we get the JIT out automatically by applying partial evaluation, one of the state-of-the-art dynamic compilation techniques. And this can be even easier as we don't need to design everything our own, as the GrioVM actually has an interpreter for evaluating LLVM bitcode, which is quite alike to us, called Ceylon. So, what we are gonna do is to add one more so-called language with the Truffle API as any other languages. This picture just depicts that. Since the P-code has so many things in common with LLVM, we are like just following their approach and get our things done. Allow me to pirate a slide from previous GrioVM's work for executing the LLVM. To execute LLVM bytecode, we need Ceylon to generate the LLVM IR, and Ceylon, what they developed to execute LLVM IR, receives the IR and uses the Truffle API to generate an AST. This AST is the base of the JIT compilation. Then this AST is sent to the JVM, where the actual JIT compilation or interpretation is happen. And for us, we are almost following the same approach, use Truffle API to generate the AST for P-code. How they made Ceylon works for LLVM is out of scope. One can always refer to their publication to get what they need to know. I myself learned a lot reading those papers, and I read their code sometimes to understand how they get things done when I get into a problem. The developing procedure is split into 4 stages. By the time of this presentation, the first 2 stages are already finished. Because of current emulation code within Ghidra does not care about the extensibility, this code can be reused, is not abstracted out. We have to do the refactor first, that's why we have stage 0. Then, a POC interpreter implemented using Truffle framework is needed to prove our choice is possible, and to learn how the GrioVM should be used. Stage 2 and 3 is the next we are about to do. Do the true JITting following official GrioVM so long. And finally, we add the instrumentation tricks to the world. Initially, I thought about we could complete at least 3 stages before the presentation, but it needs more code than I expected. Most of the time I used to learn how Griot VM, the another beast, works. That's it. That's all the things we'd like to demonstrate about GidraCraft. As for the lessons learned, Ghidra is really a huge beast that you can't handle in a short time. Sometimes the internal docs are missing, and you may cost quite some time to get why the code is written in this way, especially because it is huge and contains so many concepts. And the coding style is not quite modern. You may wonder sometimes why it is written in this way instead of some way you know better. It turns out those ways may not even exist when this code is written. But the advantage is undeniable. It is a complete thing. Many of the basic stuff you require to implement the feature or fixes are just provided. You can always refer to them to understand how things can be done. For that, I think we still need more time and a larger community to complete what we started. Thanks you guys again for listening this sharing. We really hope to have you with us. Since we follow upstream closely, it should be fine to experience the early development version. We are still working hard to provide at least a working build so you can at least feel it. And it's extremely best if you could join the development. Hope you guys enjoyed this presentation. See you next time.
Thanks a lot, Zhao, for your time and this talk about taking Ghidra to the next level. I hope you guys enjoyed it. Stay tuned for the next talk of Track 2, Make JDBC Attacks Brilliant Again, by Shuyan Zhen and Sheng-Hun Kun. Scheduled to start at 3 o'clock. We hope to see you then.
Hi there, it's 3 p.m. and time for the next talk on Make JDBC Attacks Brilliant Again by Zhu Zhenyan and Cheng Hong Kun.
Hello everyone, thank you for giving us the opportunity to tell you about our latest research into attacking JDBC. First of all, let me introduce our team. I am Cheng Hong Kun. My partner Xu Yuanzhen and I are both from the security team of Alibaba Cloud. We are responsible for Alibaba Cloud Web Application Firewall Defense System Construction, including related attack and defense technology research. In this talk, we start with the derivation of JDBC attacks, including the JDBC concept and root cause of vulnerability. Then, we will share some new ways of exploiting JDBC we found. Now, let's go. The first question is, what is the JDBC and JDBC attack? For a Java application that wants to connect to a particular database, especially relational database, it uses a standard set of API called JDBC. The full name of JDBC is Java Database Connectivity. And its meaning in the Java SQL package in JDK. JDBC drivers are silent-side adapters installed on a silent machine, not on the server. It can cover requests from Java program to protocol the DBMS can understand. JDBC drivers provide JDBC-specific implementation for different databases, such as MySQL, Oracle, DB2, and so on. For developers, JDBC helps them to share the specifics of individual databases. Now let's see a typical code for connecting to a database through JDBC. First, it loads a specific driver and then invokes driver manager's connection measure to initiate a connection to a specific database. Our following shell assumes that the attacker can control the connection URL, and we will discuss some of the attacks in this case. In the case of controllable JDBC connection, the basic attack idea is as follows. The attacker set a malicious JDBC URL and trigger a JDBC connection. Then, the JDBC silent connect to the malicious server specified by the attacker. Attackers often take advantage of some security flaw or some higher privilege feature in the JDBC driver. They trigger these problems by constructing a specific return data from the malicious server. Finally, they will result in a remote code execution or other vulnerability. Let's have a look at some of the exploits that have been disclosed and take in-depth analysis for the cause of vulnerability. Starting with the MySQL silent arbitrary file reading vulnerability. And this vulnerability is caused by the MySQL feature that has existed for a long time. The feature is that the load data local in file statement can read silent files and send them to the server. There is no doubt that this feature is very dangerous, and MySQL documentation clearly states that the silence shouldn't connect to any untrusted server. But the truth is that is always hard to be sure. And since this is the specification of MySQL, it can affect most silent, including the MySQL JDBC driver. An attacker can forge a malicious MySQL server, and after the silent connects, the silent will first send some initializing query package such as the send query package to send trust set. Then the malicious server can send a file transfer package specifying to read any file from the silent. The second one is the MySQL JDBC silent serialization vulnerability. The bug exists when MySQL JDBC driver directly deserialize certain types of data returned by the server, which can result in RCE or if gadgets are properties. Using the statement interceptor, the property provided by the driver, you can set an interceptor to perform additional operations before or after the certain kinds of statements. So, the full attacking chain is that first, set a statement interceptor attribute to server status diff interceptor class. When we auditing server status diff interceptor code, you can see that this interceptor allows the silent to send a specific query to server. In addition, the get object method is used to process the returned column. In the get object method, the driver will directly call a read object method for deserialization of branding and blob types. Therefore, the server side controlled by the attacker can trigger deserialization vulnerabilities as long as it returns falsified serialized data. Of course, the class and property names of interceptors are different in various versions of JDBC driver, as shown in the table. Okay, JDBC attack technology is usually a good attack option in the following scenario. For example, find a new gadget such as junction or fast suggestion gadgets. That's because in some getter, setter, or construction method, they will initiate as a database connection directly. With JDBC attack, we can achieve RCE or arbitrary file reading vulnerabilities. And it's easy to add this getter, setter, or construction method to the original gadget chain. Another example is some application in property export some JDBC configuration interface, such as Spring Boot Attitude. Spring Boot is one of the most widely used Java frameworks. Spring Boot Attitude is a sub-project of Spring Boot. architecture brings a production-ready feature to our application. Developers often use it to monitor their app, gathering metrics, understanding traffic, or the state of our database. There are many dangerous configurations, typically JDBC configuration, which can be manipulated by an attacker to specify the application connect to malicious database. And then attackers can exploit it with a JDBC attack. Also, the attacker technology can also be used to phishing or creating honeypots to counter attackers. Now here are some typical examples of JDBC attack. The first typical example is the WebLogic vulnerability discovered by Shi Yuanzhen in 2020. The CVE number is CVE 2020-2934. Because the JDBC configuration interface create a JDBC data source form of WebLogic backstage system has no appropriate CSRF token check. Therefore, the attacker can easily launch a CSRF attack together with the JDBC and finally can achieve an impact of RCE. In the backstage of some application also usually has the function of JDBC configuration, such as some content manager system or the backstage management system of various middleware. Like the backstage for Wildfly, the JDBC connection can be reconfigured. And because the driver for H2 is built in, you can achieve a RCE using H2 JDBC attack. Another example is when Spring Boot has H2 control enabled. We can use H2's JDBC connection to achieve RCE attacks. Attacks on the H2 mentioned above have also been disclosed. H2's JDBC while connection supports the init parent to execution and initialize in SQL settlement. In this case, run script from can be used to import an external SQL script. And using the create alias function statement in an external script allow you to define a function using the Java source code. And then we can invoke the function using the call statement to trigger the execution of the Java code. Regarding the exploiter of H2 driver, it can be noted that it requires the use of run script from statements, which is a disadvantage to complete an attack because the run script from statement, which need a silent connect to the attacker's HTTP server. This is subject to network restrictions. In fact, since H2 is an embedded database, it's possible to find an attack that doesn't require any external connections. I first found an attack that takes advantage of Groovy ST transformation to lead to remote code execution. So first, let's go back to where we started. Why we had to use the run script from statement. Even though the init property provides a condition to execute any SQL statement, but after testing, we found that it wasn't possible to introduce multiple SQL statements. And for the create edit function statement, additional call statement is necessary. So it means it takes a muni of two statements to complete the attack. But the run script from statement is used to introduce an external script to execute multiple statements. So if this can be reduced to a single SQL sentence to accomplish to remote code execution, then there is no need to get an external connection. So we went through the source code for the create alias statement and found that the defined Java method source code in create alias statement was all handed over to the source compare class. There are three kinds of processing logic in the source compare for Java, JavaScript, and Groovy. All of which are compared in order to finally execute the alias function. And Groovy's praise class catch our eye. And we immediately realized that along with Hacking Jenkins Part 2, shared by Orange in 2019, it's the same scenario and can be attacked with meta-programming. As the Orange shell, using the AST test annotation will let the developer explore the AST during computation and perform a session on the AST. As the POC show, we can exceed Java code in a sessions and praise class can trigger the Java code. However, in the real world, Groovy's dependencies are not built into H2, so this attack depends on whether Groovy companions are included into the application. This was obviously not very generic. So we continue to look for another attack. Searching in the source code, we quickly discover that in addition to the create alias statement, there is another statement that can introduce user-defined source code. And in the praising of the create trigger statement, we can call load from source method of the trigger object class as shown. We presently surprised to find that in this method, the JavaScript source code is not only be compiled but also accused. As the source code shown, it calls the eval method directly, and since script engine was finally used for execution and there was no sandbox, we could introduce any Java class we wanted in JavaScript. So with this, we can easily achieve the purpose of RCE without the need for call or other statements. As the POC shows, JavaScript start with JavaScript commands, and we can then simply use runtime's exec method to achieve RCE. Next, let's see what other database can be attacked besides H2 and MySQL database. First, let's look at IBM's DB2 database. Following the previous experience of attacking MySQL driver, we found hints about vulnerabilities are likely to appear in properties such as auto-deserialize used in MySQL. So we look through the document of DB2 JDBC driver to search suspicious properties. I noticed a property called silent root server list JNDI name. As described in the document, this program supports silent to provide additional server location after the fail in the first connection. It can connect to the standby server. And the standby server information is look up through JNDI. So it's easy to imagine that if we provide a malicious JNDI address and control the silent to fail the first connection, the silent will look up the specific malicious JNDI address. This is a notorious JNDI injection vulnerability. It can also be found in the driver's decompiled code that the context lookup measure is finally code for query. Referring to the use of JNDI injection vulnerabilities, the attacker can set up a malicious LDAP service. And when the silent connects to the LDAP service for query, it can easily complete the RCE attack using make silent to load remote codebase or other JNDI injection attack method. JNDI injection attacks are not the focus of this discussion, as virus exploits have been disclosed and are available online. And our next target is Monoshape. Monoshape is an open source implementation of the JCR specification and standard API. The full name of JCR is Content Repository API for Java. It's a specification for Java platform application program interface to access content repositories in a uniform manner. Using the JCR API, you can get data from a variety of different systems, including file systems, relational databases, and so on. A standard JCR connection for Monoshapes is in the format shown above, which require repository name to make a connection to specific repo. In this way, the JNDI string in the connection URL gets our attention. And we reasonably assumed that in addition to supporting the JCR protocol, other protocols such as LDAP should also be supported. And after trying, it turned out that you can indeed initiate a JNDI lookup request to a specific LDAP server. So this is another typical JNDI injection vulnerabilities. continue our research, we decided to try an attack on Apache Derby because it can be used as an embedded database, just like H2 database. With embedded database, it's usually easier to implement attacks because the server and center can exist in the same program. We found a suspicious code fragment when we were looking for sensitive codes in the Derby driver code. In the socket connection class, it called the read object method directly in the read message method. This method is used in Java. The read object method is used in Java to deserialize the input stream. This code fragment obviously may have deserialization vulnerabilities. In fact, from a security code point of view, this socket connection class is suspicious. You can see from its constructor method, it wraps a socket and wraps the socket output stream and input stream into object output stream and object input stream. The read message method seems to read and pressure the socket input stream. If we can communicate with the wrapped socket, we will probably be able to trigger the deserialization vulnerability. So we go back invocation chain and see whether to call the read message method. We found that the core is the inner class, master receiver thread of replication message transmit class. As you can guess from the class name and package name, this code snippet relates to Derby's ability to replicate the database. So I went through the Derby documentation session on replicating a database, and then that database replication can be initiated using connection properties. This is exactly what we want, because the connection property is controllable. In fact, if we go all the way up the code chain, you can see that whether this thread is started depends on the star master properties is enabled. As the code shows, it's star replication master boot method used for judgment. And in the code, we can find that we can specify which host the socket connect to by controlling the slave host property. So we can set the start master property to true and the slave host property to the address of the malicious server. Then Derby will try to connect to the malicious slave server and communicate. At this point, we return a malicious serialized data will be deserialized, thus achieving the effect of remote code execution. So the malicious connection demo is shown in the code. And the malicious slave server code is as follows. It's very simple. The malicious slave server can return serialized data directly after the connection is received. So let's move on. Looking at SQLite, which is also an embedded database. We trace the code for its connection and find that when the JDBC URL is controllable, we can define its resource name in the open method as shellcode. And we following into the extract resource method, we can see that the URL contracted by resource name called the open string method. So this can be used to complete a SSRF attack, such as define the JDBC URL with the shell. Using the JDBC URL can send an HTTP request to specific IP. However, SSRF vulnerabilities are not enough. Using SQLite resource sub-protocol, we can connect to the specific IP to download specific database files. So, if the JDBC URL is under our control, we can control the database files, the silent open. Based on it, how should we attack? Refer to 2019 13.3 topic stack code execution from start using SQLite. We can consider a scenario that there are controllable JDBC URL and uncontrollable stack statement. A brief code is shown in the figure. The URL is controllable, but the SQL statement executed are not controllable. In the controllable database file, there are data definition language statement used to create a table or create a view. This data definition language statement actually appear in plain text in database file. So if we inspect that the uncontrollable statement is select star from security table, we can create a view named security to hijack the select statement to execute a subquery defined in the create view DDL. In this way, we can transform the SQL statement that we can control into the query statement that we can control. Now, let's move on the next step. If we have a controlled connection, we can open the loss extension option on SQLite. So, if we have a controlled file, we can RCE by loading this extension. In fact, extension is a dynamic link library or shared object. So, in stack statement, load extension function can load a DLL or SO and its SQLite 3 extension init function. We can simply put the eval code in SQLite 3 extension init function and trigger eval code execution. But getting a managed file is not always easy, since SQLite often bursts memory corruption vulnerabilities. We can exploit this memory corruption to attack. As shown in the code above, we can use Megan's POC to create a local SQLite database file with a malicious security view. Manigans is a number of vulnerabilities that exist in SQLite caused by memory corruptions. Then, special a JDBC connection to download our database file and open it. When the code runs to query for security table, the Megan's POC is triggered to cause the JVM to crash. Finally, let's take a look at how open source software defends against JDBC attacks. Observing the previous attack method, we can find that vulnerability usually appear in some dangerous JDBC URL properties. So, some open source software takes the method of fitting sensitive attribute to fix such vulnerabilities. Both Apache Derby and Apache Dolphin Scheduler have been exposed to MySQL JDBC deserialization vulnerabilities in the past. So, they are the two open source software we studied. The CVE number for the two vulnerabilities are CVE 2021 26919 and CVE 2020 11974. The Apache Derby defends a whitelist of properties. Properties known in the whitelist are not allowed. And Apache Dolphin Scheduler removes sensitive properties from arguments. So, we want to know that is there a new exploit way to bypass property filter? We choose Apache Derby, which uses the 5148 MySQL connector version as our target. For this fix, the first idea is to see if the filter payment method is consistent with the JDBC connection processing payment method. You can see in the Derby's source code that the filter uses the MySQL connector default pressure URL method. So, by default, they are consistent. Therefore, we jump out of this idea and take a look at the overall JDBC driver loading logic. For the loading of JDBC driver, they use the SPI technology. The full name of SPI is Java Service Provider Interface. For JDBC, all register drivers are stored in the Java SQL driver file. In 5148 version of MySQL connector, there are two register drivers. One is the most common JDBC driver. The other is Fabric MySQL driver. And this Fabric MySQL driver has catch our attention. Refer to the MySQL driver documentation. You can see that Fabric MySQL driver is used to connect to the MySQL Fabric system. MySQL Fabric is a system for management of farm flow of MySQL servers. Then, we study researching in the source code of Fabric MySQL driver. If you pass in a URL that starts with the format of the code show, it goes into the Fabric driver's processing logic. You can see that in the code, the connection URL is controlled by concat by the Fabric protocol host and port payment. Trace the Fabric protocol payment. We can find that it's default to HTTP protocol. Enter the Fabric connection method. In this case, you can see that it uses the XML RPC silent. continue to follow up, we found that it finally makes an XML RPC code in the error-safe call method. And we can specify host and port of this code. So it looks like we have got an SSIF vulnerability, but it's not enough. Similar to the MySQL deserialization vulnerability, we want to see if the Fabric MySQL driver had made any errors in processing the returned data. It's clearly visible in the code that it uses the new SAXPressure method of the SAXPressure factory class. And it directly to get a SAXPressure. And the SAXPressure factory doesn't say any security attributes. So it's an obvious XML vulnerability, XML external entity vulnerabilities, which finally can cause arbitrary file reading or SSIF. So the idea of attack is very clear. We first can try a specific JDBC URL to enter the processing logic of a Fabric driver. And then we set the host and port in the JDBC URL to our malicious HTTP server. And when the senator makes a connection, it will send an XML RPC request to our server. We control the senator to return a malicious XML document. Then XE vulnerabilities will be triggered when the senator processes this XML document. We can read the corresponding files from the senator by using the out-of-band XML external entity attack technology. So the connection code of the senator is shown in the figure. We can trigger the XE vulnerability without any attribute parents. And the malicious HTTP service code is shown in this figure. Construct a malicious XML document is easy. So that's our research on JDBC attacks. It's very dangerous to let an attacker to control JDBC URLs. We recommend that if you should let user define it, you must strictly restrict the contents of JDBC URLs, including the properties and protocol and so on. So thank you very much.
Thank you, Suzhan Yen and Cheng-Hung Kun, for your talk on how to make JDBC attacks brilliant again. Next up, Mickey Jin is going to present IDA2Object, static binary instrumentation on steroids at 4 p.m.
Hello everybody and welcome back to track 2. Next up is Mickey Jin, malware analyst and vulnerability hunter at Trend Micro with an impressive track record. He created this tool to allow directly dumping multiple object files from one executable binary. It integrates with popular fuzzing engines and it seems to be pretty fast as well. Please enjoy IDA to OBJ, a static binary instrumentation on steroids.
Hello everyone, welcome to my presentation. Today, I'd like to show my new tool named as IDA to OBJ. It is designed to implement the static binary instrumentation. First, let me make a simple self-introduction. I am a security researcher from Trend Micro. My main job is analyzing all kinds of malware on Windows platform before, but now I mainly focus on the macOS and iOS platform. I started to dig zero-day vulnerabilities since last year. Currently, I have submitted more than 80 vulnerabilities to ZDI and got more than 50 CVEs acknowledged from Apple and Google. I also enjoy finding the root cause of some weird issues by reversing and debugging. IDA Pro is one of my favorite tools. Last but not the least, welcome to follow me on Twitter. My Twitter ID is Patchit. This is the background of my topic. Nowadays, many popular fuzzers are code coverage guided, including AFL, HomeFuzz, Syscaller, and so on. It's a piece of cake for open source project because we can just add some special options to compile to do the instrumentation. But how about the closed source binaries? DBI is the most choice, such as DynamicReal, Frida Scholar, and so on. But I think SBI is cooler and faster. Actually, there are some existing SBI tools, but it seems no perfect solutions yet. And I have new ideas for the implementation. So, what is SBI or DBI? The full name is Static or Dynamic Binary Instrumentation. Instrumentation means the act of adding Xcode to a program to measure its performance, diagnose errors, and write trace information. Binary means analyzing program at machine code level without having access to the source code. Dynamic means analyzing program at runtime. Static means analyzing program at compile or build time. We can see the compile instruction as the special case of SBI. So SBI is as fast as compile instrumentation in serial. Next, I will describe how I implement the SBI step by step. Well, let's start from scratch now. This is my first idea. We can load the binary into IDA Pro first and wait for the auto-analysis. When the analysis is finished, export it to the assembly file, which can be seen as the source code at an assembly level. Then, we can simulate the instrumentation process of compile. So, we got an instrumented assembly file. Finally, we can build the assembly file to generate a new binary. This is my first solution, just for PE binaries. I implemented another tool dubbed as IDA to MASM. The input and output are both PE binaries, and the assembler is the MASM from Microsoft. Now, let's export the assembly file. We can export all instructions to one assembly file by using IDA menu. File, Produce File, Create ASM File. However, MASM may cost many hours or days to assemble one ASM file. Luckily, we can use the script API to export from an address range. One more tip is, before exporting, we should use the IDA menu, unhide all. As just said, MASM has difficulty to process one big file, so we must split them into small ones. Splitting by segments is a good choice. We should manually load all segments, including header and the resource segment. Then enumerate all segments to dump, except for header and the relocation segment. Segments may share the same name, so just append their address to be unique. After the segments splitted, we need to process symbol reference. In MASM, we can use the keyword public to expose a symbol to linker explicitly. Especially for the labels, we need to note the double colons. And we can also declare the external symbols by using the keyword extern. Here is the symbol example. We can see there is a cross-reference from the pdate segment to the text segment. Then in the pdate assembly file, there is a declaration, and in the text assembly file, there is a public keyword. Note the double colons here. So, this is the processing logic. First, scan all the items from minimum address to maximum address. For each item, get all cross-reference list to its address. If there is no cross-reference, skip the item. Otherwise, make the name public. For each item in the cross-reference list, if it is not in the same segment, add an external declaration for that item. After got the assembly file, we can insert some assembly instructions to do the instrumentation. Here is the code to find the instrumentation points. Scan all functions from segments. For each function, scan all code blocks. For each code block, make a comment, instrument here, as a hint. During the post-processing of the assembly files, insert the trampoline instructions before the comment string, instrument here. Now is the time to reassembler, which is the most difficult stage. There are too many grammar errors to handle, and this cost me lots of time. I have written a Python script to do them all during the assembly file pre-processing stage. And there is another limitation for the symbol length, so I have to rename the long name to a short one. MASM is too ancient. Maybe I should consider try other assemblers. There is a longer list to tune the grammar. Here is just a small part. Note that I have to change all the short jumps into the long jump, because it may break the short jump range limitation after the instrumentation. Now we got some OBJ files from the assembly files now. It's time to link them all. This is the key issue at the linking stage. The API symbols from the import table are undefined. We must link with the proper lib files. But for some special API, I don't know what's the lib file to link with. Maybe some import symbols are from private SDKs, while we don't have the private libs. So we must generate the lib files by ourselves. Fortunately, I found the lib.exe from Visual Studio Toolkit have the function to generate lib files according to the DEF file. So this is the solution for the link issue. I just enumerate all imported models and create a DEF file for each model and write the import symbols into the DEF file. Finally, call lib.exe to generate the lib file from DEF file. After the linking stage, we got a new binary. But there is one more step to run. We need to patch the PE header, such as date directory. For example, we need to patch export date directory to make it port to the location of the symbol export dir. And we need to patch exception date directory to point to the location of the symbol exception dir, and so on. And then we need to fix the data entry in the resource segment. The data entry value is relative to image-based address. All of these fix operations are in one script for automation. Then we can run and test, but I got some crashes. There are three kinds of issues that lead to the crashes, all because of the incorrect analysis result from IDA. First is the unrecognized pointer, such as DQ offset a symbol. The second is unrecognized image-based relative value, such as DDRVA a symbol. The third is the unrecognized function-based relative value. It is a compression-encoded value for the exception handling. I will talk how to fix these issues later. IDA to MSM now works fine, but it's not suitable for full automation due to some corner case of grammar tuning. Thinking deeper, I have another idea. Let's think of the essence. A binary can be divided into two parts, the code and the date. For the code part, there are two kinds of instructions. One is the pure machine code, such as push or move. The other kind is like this: jump a label, call a function, and reference a data segment. For the date part, it's similar. The pure machine code has no cross-reference, which means it can be dumped directly. The rest instructions has cross-reference, which means it needs to be fixed for the symbol reference. Therefore, one binary can be divided into two parts the green part and the red part. The green part can be dumped directly. However, the red part has symbol references, which need to be relocated. So the key point of SBI implementation is finding out all the cross-references, which are represented by the red arrows in the picture. And the main task is to fix them all correctly. So this is my second idea. Scan all the instructions from minimal address to maximum address and record their addresses as the old coordinate system. Then during the scanning, output the machine code for each instruction. If the instruction has no reference, output is machine code directly. Otherwise, output is the OP code first. Then output dummy bytes as a placeholder, and record its address and reference type into a fixed table. During the scanning, insert the trampoline instructions before the instruction with the comment hint instrument here. After the scanning, the size of the temporal output binary file will be larger. Then we will compute the new coordinate for each instruction in the temporal binary file and record them as the new coordinate system. Then we need to fix the placeholder according to the fixed table and the new coordinate system. Finally, we got a new instrumented binary file. Next, let's review this idea. It rewrites the binary directly, regardless of the file format. So it could be cross-platform in theory. The key point is fixing all the symbol references or regulations, and it seems too complicated to implement. Let's thinking of IDA to MASM again. What does the MASM do? What happens during the build process? Why don't have to fix the references manually during the process of IDA to MASM? MASM just translate the assembly to machine code and adds the symbols to the OBJ file. Actually, it is the linker that helps to fix the symbol reference in the final binary. So, can I directly generate the OBJ files and make the linker help me to do the fix again? This will bypass the damn MASM and avoid fixing the symbol reference manually. So, my second solution comes. The tool IDA2OBJ is used to do this. The difference from the first solution is in the middle part. I will directly dump the OBJ files instead of the assembly files. OBJ file is common object file format, and this is the file structure. First is the file header and option header, then section headers. The row date is used to store the executable code and the initialized date. Then is the relocation information. Symbol table and string table are at the end of the file. After making sense the file structure, we can write a tool to generate the OBJ file. Luckily, I found a repo on the GitHub which meets my demand. Avoid reinventing the wheels. The install process is simple. Just use the pip command. And here is the simple tutorial for the Python library. First, create a module object first, and then create a section. Write the machine code to the section. Then add the section to the module. Next, create a symbol record and set its value to point to the offset inside the section. Here is 0. Then, add the symbol to the module 2. Finally, serialize the module object into the test.obj file. Next, I implement a class secDumper to encapsulate some primitives. AddString method is used to add a askString to the string table. AddSymbol method is used to add a symbol record. It will call the AddString method. AddRelocation method is used to add a relocation record. Public symbol method and a reference symbol method will call the method above. The class secDumper has an abstract method, fieldData. Code secDumper and date secDumper are the subclasses of the secDumper. They just override the fieldData method to implement the dumping logic. Both the dumpers have the similar dumping flow. It iterates all the instructions inside the segment, step by the current item size. And if the current item has a name, it will public it. Then it will compute the cross-reference list. If there is no cross-reference, it will call the API getManyBytes to dump the data directly. If there is one cross-reference, it will dump the symbol with its reference type. And if there are multiple cross-references, it will dump many symbols and with their reference type. During the dumping process, if it meets the hint comment string instrument here, it will insert the bytes code of the trembling instructions, and then increment the new address pointer. It will use the link.exe along with the Visual Studio 2019. There are several arguments for the BAT command. The first argument is the module name. The second argument is the output binary type. It's a dynamic library, an application, or a kernel driver. The third argument is the payload type. Choose AFL payload or trace payload. The remaining arguments are optional to the linker. Now it's time to integrate with WinAFL. The key point is passing the bitmap area to the instrumented binary. AFL uses the API createFile mapping to create the shared memory. Harness uses the API openFile mapping to fetch the shared memory. I just do some modifications from a good example. This is the symbol architecture diagram. One more tip is enlarging the map size when you instrumenting more modules. The function AFL maybe lock is implemented in AFL payload.assembly, which will be linked into the target binary and will be called at each code block to collect the code coverage. The main algorithm is the same as the traditional AFL further. By the way, it supports the multiple threads and multiple modules. AFL previous locations is an array with the thread ID as its index and will be cleared to 0 before each fast iteration loop. AFL area pointer is exported and will be set to the shared memory address by the harness. The harness is simple enough. Init function is used to do some initializations before fuzzing. It sets up the shared memory and named pipe. Pre and post function are called in each fuzzing iteration loop. Here is the code to fetch the shared memory address into a global pointer. Init target function will set the AFL area pointer to the shared memory address for each target module. Now, it's demo time. I will play the video recorded before. This is the demo for my tool, named as IDA2OBJ. First, clone the code. The repo is private now. I will open source it later. I just put the code on the desktop. Then create a workspace, such as demo. Then copy the target binary, which you want to fuzz, to the workspace, and then load it into the IDA Pro. Note that you should choose menu load and load resources. It asks me whether to load the PDB file. Yes. The tool still works without PDB. Okay, auto analysis is done. Then execute my script. First, I want to execute libimports.py to generate the lib files. Done. Let's check the lib files. We can see there are 32 lib files, which corresponding to the import table. Check this one. These are the import symbols from the import table. Next, execute the script to dump the OBJ files now. Select main.py. Okay, the dump is finished now. Let's check the OBJ files. Yes, let's link these OBJ files into a new binary. Just use the link command. We will see the new binary is generated. One more step is to patch the binary. Okay, the patch is done. Let's load it again. Then we will try the new generated binary for fuzzing. Just back up this one. Replace to before the fuzz, we can use the command to check the instrumentation. Yes, we can see captured 794 tuples. Next, we will test multiple binaries. And this plus. Okay, we can see we captured more tuples now. Then run the fuzz command. The R disk is the RAM disk I just created. There are 4 copies. And make the output auto directory. Then run this command. We can see the fuzzer is running now. Before ending the demo, let's check the new generated binary. We can see in each code block, there is a piece of tracing code that call ACL Mapilog. And this is the code we write in the payload assembly before. Thanks for watching. Okay, let's come back. Let's make a summary. First, I just let the linker help me fix the symbol references. However, the linker also generated some redundant state, such as the PE header, which makes me can't reuse the old PE header. Maybe I can hijack link.exe and only exploit its functions of fixing symbol relocations. Second, it could be cross-platform in theory, but I just make it come true for 64 platform PE. It is as fast as the compile instruction with the source code. Finally, the new binary could be equivalent to the old one, only if all the cross-references analysis is right. So, the real challenge coming. The challenge is the precondition of the solutions is that the analysis result from IDA is correct. However, for some reasons, sometimes IDA can't recognize some pointers or relative values, and it may lead to some crash issues. The solution is creating assistant scripts to help IDA analyze before exporting. The script is used to scan suspicious pointers from data segment. It reads a keyword value. If the value inside the PE address range, then it is a suspicious pointer. This script is used to help some relative values. There are some image-based relative values not recognized, many existing in the jump table of switch case. The fixed logic is a bit of complex. Maybe you will cost some minutes to read it. But now, let's check the fixed effect. We can see the difference in the red rectangle. It was the immediate value before, and it will get the correct cross-reference after the fix. IDA is supposed to analyze the exception handling data structures since the version 7. However, there are still some data structures that can't be recognized. Maybe because of the undocumented data structures. There are some function relative values in sh4. The core logic of the script is writing a parser according to the referred header file. Here we can see the data reference is recognized correctly after the fix. C++ frame handler 4, dubbed as FH4. It is a new feature to reduce the binary size of C++ exception handling on 64 platform. Some function relative values are compressed and saved into RDate segment. The relative values will be larger due to the instrumentation. So it means the RDate segment could be enlarged too. It compressed the value into 1 to 5 bytes. Depending on the value. These two functions get net encoded and decompression are used to decompression and compression. The solution is simple. I just rename the compressed location to the concat of a hint string, fix me, and the two targets address string. Then update the real value when the target address changed. Takeaway. I just introduced two static binary instrumentation implementations. One is IDA to MASM. The other one is IDA to OBJ. And then I introduced one SBI algorithm. It just rewrite the binary directly. It could be cross-platform in serial. And it is not implemented yet. Then I wrote some IDA Python scripts to assist the analysis. The repos will be open source later. They are private now. Future plan. First, maybe I will do some bug fix. Welcome to report issues and pull requests. Then I will try to integrate it with other files. Finally, maybe I will try to make the cross-platform idea come true. This is the references list. Thank you. If you have any questions, you can touch me on Twitter or email me at mickeyjin@trendmicro.com.
And this brings us to the end of this talk. Big thanks to Mickey Jin and thank you all for joining. Meanwhile, you might want to hang on to your infrastructure because next up is Gao Chin with his talk going deeper into Snyder Modicon Pack Security. Please
Ladies and gentlemen, welcome back for the last talk of track 2 for the first day of conference. You are gonna hear from Gao Jian, and he is gonna talk about going deeper into Schneider Modicon PAC security. I hope you all enjoy.
Hello everyone, this is Gao Jian. I'm very glad to be here and share my research findings at HITB Singapore 2021 today. Really appreciate the opportunity. The topic I would like to share today is going deeper into Schneider Modicon PAC security. Before I begin, I would like to reintroduce myself real quick. My name is Gao Jian from Xi'an, China, currently an industry control system security researcher and NS focus. The research mainly focuses on PLC, design, SCADA, industrial equipment, and system. Work includes things like vulnerability modeling, industrial field security testing, and evaluation. For the past few years, I reported several vulnerabilities to Siemens, Cosys, Schneider, and so on. Got dozens of CVEs and FOCO, and of course, success notes from these companies. As well, I have shared my research at several conferences. This includes ChinaConf, SDC 2020, HITB AMS 2021, SS Cybersecurity 2021, and so on. If you have any questions or ideas regarding the security aspect of our industrial control system, please feel free to contact me. Here is my email. I'm looking forward to your emails. Please allow me to introduce our lab, Go Lab, which focuses on ICS, IoT, and Internet Internet of Vectors-related security issue. We won the second prize in the Robot Agent Challenge 2018. Jigbang. Our long-term work in SS vulnerability research results in finding over 53 vulnerabilities in 2020, involving Siemens, Schneider, ABB, Cook, and other manufacturers. In addition, we participated in various competitions such as Fly On and got good results. So here is the outline of today's presentation. First of all, I will introduce the multi-compact range of the product application scenarios, the architecture and function of the high-end M580 family, the security aspects of it, and so on. In the second part, I will introduce the Schneider Priority UMass protocol, its script mechanism, function code, and so on. Next, we will explain fast-related knowledge and for UMass protocol, include how to select samples, how to build further program, and give you the process of the successful fast demo. The fourth part will be the most interesting part of this presentation, where I will show you how to break through the M580 password protection mechanism, which includes authorization algorithm, integrity checks, and format of special function codes to perform sensitive operations such as start and stop the controller. In the next section, we demonstrate a potential ransomware attack on multi-compact, including the authorization bypass of the password protection, replacement of the password of attacker's choice, remote code execution, cause permanent damage to the controller, and a brief demo of the attack process. And last but not least, I'm going to talk about how to protect against such attacks. Multicon is the first name in programmable logical controllers. The inventor of the PLC, Multicon introduced the first PLC, the Multicon 048, in 1968. This innovation changed the process design, moving from completely hardware-reliant system to automation system, reducing the time, effort, and cost previously associated with the modifying a process. The following years, Schneider helped expand the reach of the Multicon technology worldwide. Today, the Multicon family continues to push boundaries and define the technology that enables and connects modern machines and processes. The Multicon family of PLCs and programmable automation controllers still stand for innovation, offering a full range of solutions to meet your automation needs. To provide an economical way to deliver function control in gap between the PLC and DCS, Schneider offers industrial process automation controller Multicon paths. Multicon paths feature redundancy, functionality, negative internet, embedded cybersecurity. Schneider is targeting the PAC towards process end user, particularly end user who are currently use the large PLC or PAC-based system in energy-intensive industries, such as water, wastewater, food, beverage, upstream and midstream oil and gas, and metals and marine. The ARM microprocessor used in the M580 PAC is the Spire Drunko multifunction CPU built by ST Microelectronic through a partnership with Schneider. The operating system is the Wind-River VxWorks. On the high level of the OS runs encrypted firmware, on the top of which run users' applications. M5HA also provides rich third-party communication functions such as Modbus TCP, Ethernet IP, FTP, HTTP, and so on. To address today's critical cybersecurity issue, security is built into each M5HA pack to provide an open yet fully secured system. Advanced cybersecurity features help ensure the system are protected from cyber attacks. Each M5HA pack can be secured using encrypted logins and passwords for every application. Unnecessary devices can be disabled and checks can be performed to verify the integrity of the continuous programming tool and firmware, as well as the normal behavior of the system itself. Based on the previous introduction, we can summarize the attack surface of pack series products. First of all, the support of the numbers of third-party products make interconnection quite easy, but also introduce risks. For example, each protocol opens external port, which may be bad and taken advantage of by malicious attackers to perform unexpected operations. These protocols include privacy protocols supported by pack products, HTTP, FTP, and so on. In recent years, many vulnerabilities have been exposed in protocol stacks and operating systems. Therefore, the use of third-party protocol stacks and operating system could potentially bring more serious problems. A vulnerability in VxWorks will affect thousands of devices. Also, physical attacks should not be ignored. M5HA is equipped with USBs. Attackers targeting this kind of hardware interface can't be ruled out. We focus on two potential attack vectors in this presentation, though there are many more research aspects. 1. Privacy protocol. The reason being that after many research work we find out weak privacy protocols are often the best way to break and damage critical infrastructure. Also, ports in privacy protocols normally can't be turned off. When you get hands on a device, it's designed to have ports open to support privacy protocols, and you can easily access without any extreme configuration. Second, the password protection mechanism. Many industrial control devices has its mechanism. Sadly, not many people use this feature in the actual field, despite it being really critical to overall security. Activating this feature will prevent potential unauthorized access and attacks, but nothing is perfect. The password protection mechanism is not an exception either. We conducted several research regarding this feature and gave a presentation on HITBSecConf2021 about the how to bypass such mechanism for Siemens Symantec products. Links are provided here. In this presentation, we will dive into the issue of authorization bypass in Schneider's most high-end pack product, the M5HA. Before we start, here is our research setup. The configuration software is a Control Expert 15.0 SP1. The firmware version is v3.2 and the hardware version of the M5A3 is EP581020. Environment configuration. One PC is installed with the configuration software, and another PC is used to compute paths and write scripts. After connecting to the switch, the two PCs exchange information with the M5A3. Let's start with the first technical part. The privacy protocol for Schneider M5A3. The privacy protocol used by the configuration software to communication with the M5A3 is UMass. Unifilled Message Application Service. This protocol is used by Schneider to configure and monitor the communication between the software and the PAC system, not only in the M5A3, but also in the M340. UMass protocol is based on the Modbus TCP protocol. It's extended on the function code 0x5a reserved by Modbus TCP protocol, and forms its own complete protocol processing system. Next, let's take a look at the UMass format. It's the function code and data part of the Modbus TCP protocol re-encapsulated. The UMass request packet starts with the 0x5a identification byte, followed by a 1-bit reservation flag called sensor key. After this, in the specific function code of UMass protocol and the date section. UMass function code varies in different formats, including ID, offset, length, and others. The UMass response package is basically the same as that of the request package. It starts with the 0x5a identifier. The next is the sensor key, then the 1-bit error code. It will return FE if the request package can be correctly processed by the controller. The error code is followed by the rest of the data in the response package. We obtained the function code list inside UMass by reversing engineering the firmware of M5A3, which contains a variety of different operation function code categories, such as operating PLC information, reading a block, writing a block, begin upload, and so on. There is a screenshot for some of them with the descriptions. In this list, some function code require section keys for operations, some don't. So, how is the section key generated? Through analyzing the package, we learned that the reservation on process of the section is like this. Firstly, the client sends the PLC reservation function code 0x10, and the PLC will return a correct reply package. The FE in the reply package is followed by a bit, which is the section key. In the following package interaction, the sensor key must be encapsulated into the corresponding position so that the PLC can handle the operation corresponding to the function code. To facilitate the analysis of the UMass package. We wrote a simple UMass freezing plugin, which is written in Lua and imported to Wireshark. This enables us to have a clear look at the UMass structure, which contains the culture section key, function code, and data section. By analyzing the UMass protocol, it's found that the structure of the protocol and the procedure matched process is simple. It only needs to send the 0x10 function code and wait for the pack to return the correct reply, and added the 1 bit to the section key position to establish the correct later on. With such a simple process and message format, are there more vulnerabilities? We then conducted the fast testing against the UMass protocol, where we chose the bootfast framework and were careful to keep a backup of the fast process traffic in case of the problem reproduced later. In the fast process, we also added a power control unit to improve the fast efficiency. In the fast process, calls the pack into a fault error mode, which will stop the whole process. The power control unit will restart the pack again after the execution of fast program, so that you can improve the fast efficiency to achieve the automation of fast process. Before fast, we need to select samples. We divide all functions code of the UMass in two parts. One that requires section key and the other that doesn't. This separation helps us to use different modes for quickly fast. The next step is how to build our fast program. The first step is to construct UMass protocol packets, which differs for different function codes, but the basic method is the same. The other thing is to notice here is that if you need a section key, you need to do something special in order to do a wild fast. The second step is to set the section object. A third step is to configure the fast target, including the IP address, port number, timeout, and protocol type. Stanford and target to the program with the monitor and power control modules. Here is a simple fast demo. We found a denial of service vulnerability around 100 seconds that put the device into critical failure mode and require a controller reboot to recover. Okay, let's see it. Oh, the PLC is stop stated, and the fast is running. You can see in the below, the PLC, the PAC turn into a critical failure mode and required a controller reboot to recover it. Here are some of the vulnerabilities we discovered using our own fast program, which was discovered in January 2020. Okay, moving on to the second part of today's presentation. When we reported a number of the vulnerabilities to Schneider in 2019, Schneider said that they were not vulnerabilities and that they would not exist with an application password. And this time, we found that when the application password is set, the application program compiled and installed the PLC will have password protection, hence unauthorized access will be refused. But what is this password protection mechanism? How to get around this authorization mechanism? So we start this part of the research in 2019. Let's see how we bypass the authorization step by step. The first step is to confirm how the password is stored. The second step is to understand what is the mechanism of the password protection and what algorithms are used. Step 3. After we bypass password protection, is there any other security measures? And if so, how we can break through? Step 4. After all the obstacles are broken, how do we flag a client to perform sensitive operation attacks on the PLC, the PAC, or M5HE? Take a look at the first part and find out what form your passwords are stored in. To find out how the passwords are encrypted, I reserve the Unity encryptor.dll file. The encrypted password is delivered in two parts. The first part is an 8-byte random key, which is randomly generated as the result of the hash algorithm. The second part is the value of the SHA-256 using the password and the salt. This result gathered with the salt will be stored in the APX project file through base64, which will then be downloaded to pack with the project files. The second part is the value of the SHA-256 using the password and the salt. This result, together with the salt, will be stored in the APX project file through base64, which will then be downloaded to PLC with project files. The second step is to figure out the password protection algorithm, means the authorization algorithm. Here, we analyze the authorization process in M5HE firmware to understand how the authorization mechanism works. First, the client randomly generates a 32-byte random value and sends it to PAC at the request date. The PAC responds with a 32-byte random value PLC random key. Finally, the client obtains the follow authorization hash through the SHA-256 algorithm based on the input password and two random values. After the hash is delivered to the PAC, the PAC will verify it. So, the key to get around authorization is to find the password salt hash. Where can we get this key? Luckily, we found the password salt hash in the traffic. After analysis, control experts will read the pack's password hash before authorization, and the pack will return the password salt hash to the client, so that we can bypass authorization by using this leaked password hash and carried out any operation on pack, such as start, stop, upload project, and download project. Too simple to be true, right? After testing out, using leakage hash solely to complete the authorization process failed to conduct any sensitive operations, even with the CC key. What was the problem? By observing the traffic between control experts and M5AT, it's found that a large number of 0x38 packets appear after authorization. The format of the packets is significantly more complex than that our traffic without password protection. Maybe it's the injection of the additional security measures. After our analysis, it's found that the 0x38 function code is a security function code, in which the redundantly part acts as an integrator verification. The integrator check algorithm is shown in the diagram. First, the PLC identity is obtained. It's a unique pack identifier and can be read through the 0x02 function code. The 32-byte proprietary value in the data package is calculated by SHA-256 multi-chance. UMAS MSG is the message body of the UMAS protocol. Upon successful authorization, UMAS traffic is added with a 32-byte integrity field, and communication with the pack is done through the 0x38 function code. Here, we take a look at the message format of the 0x38 function code. First, 0x5A and section key parts remain unchanged, followed by the 0x38 function code, followed by security mode 01. The calculated 32-byte integrity field will follow, and finally, the full format of the original UMAS message. The section key function code is included. Below is a screenshot of the Python implementation 0x38 function code. Now that we have covered all the procedure for all password protection mechanism, let's summarize. First, we can obtain password hash via UMAS command memory block reach 0x20. Second, generate 32-byte client random key and then receive challenge key from pack. Calculate the correct hash value. Third, take PLC reservation via UMAS command 0x10. Fourth, we need to add a socket layer of integrity check of the 0x38 function code to all the original you must message bodies and send them to the pack at this time. We can perform various sensitive operations: execute, upload program, download program, stop, start, and so on. We were faced with the final problem. Of how to make a client to conduct sensitive operations. First, we use the script to achieve the authorization algorithm and integrate the algorithm described above, then conduct the HR process of authorization and security paths, and finally integrate the start and stop packets into the script. Here we provide a demonstration of a reply attack. The target is a password-protected M5AT. It's impossible to start and stop operations without the correct password. After running our reply attack scripts, the pack can be manipulated to make it in any stage run or stop. Okay, let's see it. First, we should check the password can be set. If you put in a wrong password, you can't perform stop and start. Okay, running our reply attack script. You can see the pack can be make any stage run or stop. Yeah, now the pack is in run stage. So let's continue. In recent years, there can be a variety of ransom incidents. However, these attackers are targeting either the IT lab in ICS or the servers or PCs in OT environment. Is there a possibility of a ransomware targeting level 1 containers? There will be. We have proposed such an attack on the container. Let's see it. To perform this new type of attack targeting Mollycon pack, there are 5 steps. First, invade the OT network. Search for M5H devices in the network and confirm the attack target. Second, replace the application of the M5AT. Hijack the origin production process and set the attacker's known password. Third, injection shell code to remotely control the controller of M5AT. Fourth, synchronize send ransom email to enterprise managers, demand a ransom. Fifth, if not paid on time, remote start an M5AT device damage command or instruction. In this attack mode, there are several key technical points in this new attack mode, including applications that bypass authorization and replacement it with a password known to the attacker, and how to perform remote code execution on the M5AG. We are going to demonstrate this tool in a bit. Let's see. Let's start by looking at how to bypass authorization by replacing an application that contains an attacker's known password. Here, a weak password is set just for the sake of the demonstration, whereas in the field it could be too complex to be correct. First of all, let's see it. First, check the version of the control expect. Next, confirm that the pack can set a password. Only the user of the correct password can access the pack to modify the program or monitor the PLC. After running the attack script, the application program in the pack was replaced by another machineless one that has nothing to do with the control process, which contains different password. Hence, the original password can't be used to access the controller anymore. You can see the wrong password you input. So, access to the controller and program modifications will now require the new password. The new password is we download the project with 1, 2, 3, 4, 5, 6, 7, 7, 8. You can see if we input this password into the pack, you can perform stop and start. Okay, let's see how we can achieve RCE on M5AG. We can write physical memory of the pack while you must command 0x28 and 0x29, but can't write code segments directly due to page protection. So, we can modify the function pager in memory to hijack the control flow, use ROP techniques to complete the code execution. Okay, let's see the demonstration. This is a simple demo for the RCE attack. It opens the internal VxWorks WDB debugging interface with a port 171H5 on the M5HA, as shown in the above video. Let's see it. First, use Nmap to scan the debugging port, which turned out to be closed. You can check it. The port is closed state. And next, run the PLC script. When the PLC is running, use Nmap to scan the M5AG again. Okay, you can see at this time the port 171H5 is turned on. It's the open state. Okay. Now that we could see a potential attack of this kind. How can we prevent it from happening? We will elaborate from the following aspects. First, we should be able to identify the critical function code involved in dangerous operations and proper runners in our protection devices. For example, and runners to identify check PLC reservation function code 0xchain in the industrial firewall. Once such packets occurred during normal manufacturing, the traffic should be blocked immediately. Second, we should also focus on the management of our ICS environment. To begin with, all the PLC maintenance personnel should be reliable in case of an insider attack being performed directly to the running PLC. Adoption should be performed over all operations against the ICS system to prevent malicious maintenance operations, as well as all traffic involving critical device so that potential threat could be identified. An access control list can also help to reject access from untrusted IPs. This function is supported by M5HE. You can open it and enable it. Third, for ICS manufacturing, not only Schneider and Siemens, many priority protocols are really weak with such simple authorization algorithm. Therefore, manufacturers should pay attention to the following aspects to stressing the container security. There is some suggestion of we can say it. First, and mature authorization mechanism for priority protocols. Second, use strong encryption algorithm. Third, avoid information disclosure. Fourth, password authorization should be performed in PLC or PAC. Fifth, sensitive information should be stored in a trusted zone where it is reinforced. Okay. Actually, there is no standard for PLC coding. VVK and Sarah lead the PLC Security Top 20 list project and released the first version on June 15. It's a pleasure that I was invited to join the core group of this organization to discuss project on PLC security coding. Well, PLC security coding can't solve all the network attacks. It can solve many problems caused by misconfiguration or insecure heading of users' inputs and so on. And at present, this project still has a lot of work to do, including top 20 secure PLC environment practice, and the PLC security top 20 list the version should be upgraded Anyone who is interested in the topic is welcomed, and we look forward to your joining. Welcome to join us. Okay, that's all for today's presentation. Thank you all for joining the talk. If you have any question, please feel free to contact me. Thank you. Bye-bye.
Gao, thank you very much, everybody. I hope you enjoyed the last talk of today, and I hope to see you all back tomorrow for another set of wonderful talks. Thank you very much, and have a nice evening.
can't